Good morning. Welcome to Digital Gravity Lab. Thank you for joining me for another one of my walkthroughs for my homework in Computational Science and Engineering at Harrisburg University of Science and Technology. So I am actually going to break up this next assignment into one or more videos simply because there are multiple modules and I want to make sure I cover everything well and get things submitted on time. So walking right into my assignment here, my assignment was to build a UI that categorizes graphics cards based on whether they're single instruction, multiple data, multiple instruction, multiple data, etc. So a Flynn classification simulator, and as well as implement and time some various processes. Based on that, I'm using my computer. So got ChatGPT to help me write a whole bunch of code, made a bunch of modifications back and forth, etc. In order to automate that, and so I pulled in a few dozen different cards here, and looked at, desktop CPUs, this whole different graphic cards, radar pipeline, multiple instruction, single data, various arrays based on this, and it gives a little bit of info underneath about a card. Also had a fun little thing here, auto detect my GPU, so I can click that, pulls up. I've got a 5080 graphics card, and it's a hybrid single instruction multiple data or multiple instruction multiple data, depending whether you're talking about it at the micro level or the macro level. But yeah, so there's that little fun gizmo there, and task to implement and time. So building a bunch of CUDA code here. You can see the CUDA JIT here. So just scrolling through various grids and processes, different variants that it pulls, and here you can see the different run times as the data got larger. You can see the GPU, all that overhead, but very quickly got faster than anything else for larger data sizes. And the serial loop, you can see there that that straight process of time as it runs data. It takes about the same time no matter how much it's doing. But as you add more, it takes more time, but each individual element, the average is still the same. But you see that GPU, that average really drops down as you get larger data sets. And the vector, that speed up for the GPU versus the single instruction, that's serialized, whatever. You can see GPU as it gets large sizes just really kicks everything else out of the water there. So there's a serial Python, that single instruction, single data. There's a single instruction, multiple data, a NumPy, and then multiple instruction, multiple data, also threads, and then that single instruction, multiple data on the GPU, where it splits it in a whole bunch of different pieces and processes that data. So yeah, very, very interesting how it does that. That was the one. That was the first. Of course, I had the same intro things as my last assignment. Make sure everything was set up. Pretty straightforward there. Okay, so the next one. One or two other minor changes. Adding pandas and VTX in order to look at a few things in this, but so direct task, build a latency heat map across 3 number zones. We'll say that direct task there is kind of impossible on a GPU on a Windows computer. Though the CPU does have 2 domains internally, you can't access them, so it really is just one. There is that, and then some good to compare. So I'm going to scroll down here. You can see some various latency things that it pulls versus local or remote. Got some CPU, the first access versus second access for a GPU kernel. It's a lot faster second time. So we did this whole heat map here. Unified memory on demand, unified prefetch, speeds up some, explicit as well for the explicit kernel. You can see the time scale is just drastically different. But the end latency was less, but yeah, all depends. Effective bandwidth. You want higher bandwidth, lower latency. So unified memory on demand is the best, particularly when you're much larger data sets. Otherwise, it's when you're less than a megabyte, or a lot less than a megabyte, doesn't matter much. When you get closer to megabytes, it starts making a difference. The other task 2 is compare CUDA managed array versus explicit host device copy. So there's a bunch of different things that had to be done there in order to get that to work. Showing this first run there, second run, managed. You can see there that manage is just a lot slower versus the explicit So the explicit versus unified memory, that unified managed memory is just a lot slower. And part of that had to do with it's sending many smaller copies versus one large one, which just makes a huge difference. So trying to visualize that in some various GPU processes and launches. It was a lot of work. But you can see there are different times and whether CPU, CPU callback after GPU, you can see it, how many reads versus launches there were as well, and that time scale there. Again, how many passes, megabytes it was, the total time, and then using the timing graphs for that in order to compare those, but also then look at the page faults. So when there's a lot of page faults, it's a lot slower. The other thing for doing that, which took quite a few hours to figure out, is setting up end site systems. That's really the way you look at different page site faults and whatnot within the system. A lot of different ways. Tried doing it, but what it ended up being in order to get that to run is saving a file as a Python file using this PYL installer in order to turn it into an exe file, and then loading that within the NVIDIA Nsight system. So you have all these different reports that it's looking at and running as you would load that that file. See there, here's the explicit file, all the different process it runs, when it's blocked as it runs the process, versus when it's pulling very CUDA's cores, the CUDA API. Alright, here's that CUDA memory allocation managed system call right there. Yeah, various CPU usages as it transfers over, right? All the different call stacks that this managed state had to pull, different frames. Yeah, so a lot to unpack on understanding more about how to view this, but that is how you visualize paste faults, migration patterns during the whole process, using that CUDA managed pair as CUDA managed array as well in that. But that is that whole program there. And unified virtual memory is most desirable when programming productivity and portability outweigh raw performance concerns. And then you also got thread pinning as another way to help mitigate NUMA penalties by ensuring threads consistently runs on the same CPU core instead of bouncing across different CPU cores, and make sure it accesses that memory local to its NUMA core. But as I mentioned, on a Windows computer, you effectively only have one that you can see. There are those performance cores, so there's kind of two NUMA zones in the desktop, but that is not something that you can manage really at all or see very well outside of switching to Linux or doing it in Google Colab. So there's a few other features that can be seen on Google Colab, but that said, Google Colab doesn't have Insight systems, so yeah, it's a give and take between the two. And last thing to show now, set up some MPI process that had pulled in using that MPI for PY, importing the MPI was really the big change up here. So the task here is measure latency and bandwidth across message sizes, and then to log some overlap with SQL, sequential send, receive, and plot results. Got as close as we could to that. Let me actually rerun this kernel. Here. Alright, so load everything. You can see that thread ping pong round trip. So in order to get this to run, I actually had to save this as a PY file and pull it up in prompt, loading it that way using the MPI exec to load that file. And then you could see as the transfer size increase, you can see that size increase in the bandwidth. Really was still working on figuring out that log over kernel overlap and that sequential send receive, but there's some plotting the results here for what we've got now. So that's what I've got now. Thank you for joining me. I look forward to your questions on anything, but we will jump back on in more exercises in the future. So thank you for joining, and I'm Matthew Isler with Digital Gravity Lab. Thanks.